Um, okay, so I said that I'm going to do something today, but I won't. But let me just repeat. Sorry, cable is not connected. All right. So let's just remember what we have done the last week. I mean, I have been solving this problem. It's like three oscillators, but three particles which are connected by springs in such a way that well, they have this symmetry group of D3, which was basically isomorphic to S3. And this was an abelian. This was not. This was a non-abelian group, and so therefore it had like a two-dimensional representation. So we have talked about this. And in that case, I have said that there are like three modes in here because there are three particles. Yeah, it's three particles, and each particle has only 1 degree of freedom. It can only move tangent to the circle. And so as a result, there are three modes in here. Okay, but one of the modes, let's see. I mean, there was this representation in here. I forgot what the name of the representation is. But let's remember that the first representation was U2. I mean, we have decomposed this into these two representations, U2 and U3. This was the signature representation, if you remember. And this was some kind of a two-dimensional representation, okay, if you remember. But if you don't, then no problem. I mean, the trivial representation doesn't appear in here because somehow a displacement like that, this is not going to be left invariant under a reflection by this. So therefore, the trivial representation doesn't appear in here. I mean, if I include this vibrational mode where the particles can go radially outward, in that case, trivial representation will also be in the picture. But for the tangential displacement, we don't have this one. But instead, we have the signature representation. In any case, whatever it is, it doesn't matter. It doesn't change the actual picture. So we have said that this is the representation where the corresponding displacement pattern, the mode displacement pattern, corresponds to a uniform rotation of all of the molecules, and this has frequency 0. So that's basically conservation of angular momentum, I said, conservation of angular momentum. I mean, we know that there's some kind of a rotational symmetry, whatever. We know that the angular momentum is conserved in this case because of some physical reason. I don't want to go into this. So as a result, this implies that if they are given some, I mean, all of them are given with some angular velocity, with the same angular velocity. In that case, there won't be any compression or extension of the springs. So the springs will be in normal lengths, and so as a result, this will continue rotating. And I said that this is like an oscillator with frequency 0, with no restoring force. In a way, I mean, you can think of it as some kind of a limiting situation. You can place an oscillator for that mode, but when you set the spring constant for that oscillator, when you take the limit where the spring constant goes to 0, you get this free particle thing. Whatever. For this one, this is two-dimensional. So as a result, these two modes are somehow, they are convertible to each other because of some symmetry operation. So I have said that the modes are these. So let me kind of show the particles like that, okay? This is the mode where this particle goes like that, and that particle goes like this, and this particle doesn't move, right? That is one of them. This is one oscillation mode. So as a result, if you just set the particles in this mode, it will just oscillate. I have called this oscillation frequency as omega 3. Let's call this as omega 2, right? The frequency is omega 3, whatever it is. And I think I have also found the value, but it doesn't matter what it is. The value is not actually relevant, right? So, right, this is an oscillation mode, which means when you start oscillating these particles in this mode, they are going to stay in this mode forever, right? It's not going to change. So as a result, this first particle in here will always stay at rest, and this will always be oscillating back and forth at this location. And that's it, right? And there's another mode, which basically is obtained by rotating this mode by any of the symmetry operations, anything actually, you're going to get one of the other modes. So it is this mode in here. Let's see, where this is at rest, let's say, and these two are oscillating like that, okay? And because of the symmetry, this also has this omega 3 frequency. Well, you can say that you can continue, right? You just rotate one more times, and then you're going to reach to that mode. Let's see, this one in here. This will also have the same frequency, but somehow it appears that this is just a linear combination of these two. So let me just say it like this. I mean, if I express it with some kind of a vector in here, let me call this as, I don't know, let's say F1. So this basically corresponds to some kind of a 3 by 1 matrix, right? This is the mode pattern expressed mathematically. Let's say that this corresponds to F2, and this corresponds to F3, let's say. What I'm saying is that these three modes are not linearly independent, so F3 is basically equal to F1 plus F2. Is it? It's the negative of, yeah, whatever, it doesn't matter. Minus, all right? So their sum is equal to 0. Whatever. So as a result, there are essentially there are only two independent modes in here, having this frequency. Again, each one of these modes is a mode, right? If you just start oscillating in that mode, it will stay in that mode forever. But there are many different modes having this property and oscillating with the same frequency. Moreover, let's say it like this, any linear combination, let's say, any linear combination, let's say C1 times F1 plus C2 times F2 oscillates, is a normal mode. Each one is also a normal mode, oscillating with the same frequency. I don't know, that's equal to omega 3, right? Let's say it like this, right? So as a result, if you have two normal modes that have the same frequency, you can take linear combinations of them, and you still have a possible normal mode as well. So as a result, I can count the normal modes corresponding to that, I don't know, that thing in here, that frequency as this mode plus that mode, but somebody else might actually count them as this mode and that mode or whatever. So as a result, there are many different ways of expressing these two normal modes in here, whatever you choose. So let me just show it symbolically like that. So I can think of a normal mode in here. Let me, sorry about this. I'm just going to show the particles in here. Let's say that this oscillates like that, this oscillates like that, but this one oscillates like that. I mean, this displaces like epsilon, this displaces like epsilon, but this one displaces like -2 epsilon, for example. This is just a linear combination of these two modes, okay? So therefore, this is also a normal mode oscillating with the exact same frequency, okay? So that's basically a consequence of the degeneracy of the normal modes in here. We have the same kind of a thing in quantum mechanics, the degeneracy of the energy levels. So that means like, I don't know, let's say 2px and 2py, for example. These are degenerate energy levels. You can take any linear combination of these energy levels and still you get an energy level with the same energy, okay? And we basically have the same kind of a situation in here. So it's not a property of quantum mechanics or oscillators, it's just a property of linear algebra, right? We have some matrix which has repeated eigenvalues, okay? But now we have a physical interpretation for it. Okay, I don't know if you have any questions in here. If you have, yeah, you can ask. So in any case, I'm just going to continue to something else, right? So these are some toy problems. Then we can talk about some realistic problem like the vibrational modes. Of the water molecule. Okay, so this is from John's textbook, actually. It's an example that I took from John's textbook. So, I mean, since I like this example a lot, because this is actually a physical application of what we have learned so far on a concrete physical molecule, right? So as a result, in the past year, I have done this example completely, actually. I have just expressed the representation and then decomposed it and then whatever. At the end, I have identified all the normal modes, more or less, in the way that we can identify by just using group theory only. We have nothing to do with the real water molecule. In any case, this is actually done. So as a result, I don't want to do it in here, right? I don't want to repeat again in here. I'm just going to describe in general what's going on in there. But there are past videos. I have also placed them on separate playlists. Let's say, see the videos on vibrations, right? So there are actually, I don't know, about 1 hour long, I think about 1 hour long video that describes what do we do to actually find the vibrational modes of the water molecule, okay? So just see it, but I'm just going to just give a general description in here. So we basically have a water molecule is something like this. So I'm just going to show it like that, okay? I think I'm going to do it like that. So the molecule, I think this is a cartoon in a way. Right, it's something like that. I think probably this is better, right? In any case, we have an oxygen atom in here and 2 hydrogen atoms in here, right? And then somehow, this is the cartoon picture, we just connect them with a line that kind of represent the chemical bond between hydrogen atom and the oxygen. Whatever, there are also electrons and whatever in here, but we forget about the electrons and just concentrate on the motion of these 3 particles. This has a mass, MO. These 2 have masses, MH. Right? So it has a very nice symmetry group. So we basically look at the largest possible symmetry group, actually. So as a result, we just look at these symmetry operations. So we can easily identify some of them. So the first one is this. So I'm going to draw some kind of an, yeah, let me first of all draw this x, y, and z axes, right? So that's the x-axis. I say this is the y-axis, and that's the z-axis. So this is three-dimensional. The molecule is two-dimensional, but when I'm expressing the symmetries, I'm considering all possible elements of this three-dimensional rotation group SO3, right? Because the larger the symmetry group, the better you are going to, yeah, well, you're going to have the better analysis, right? So you just find the largest symmetry group in there. Okay, so the first one is basically a rotation around this axis. Right? So that's what we call as A. So that's a 180-degree rotation around. I think I can call this as the y-axis, but let's say that this axis in here. Okay. So that's A. So in addition to that axis, there is also a plane, which is essentially a YZ plane. So let me show it with a pink color. Is this pink? Yes. So I can think of it like this. So this is pink. So there's a reflection across this plane, right? So let me just write it in here. So reflection across this mirror plane. This is also a YZ plane, but essentially this changes x with minus x, right? So it's basically a reflection along this horizontal direction. Okay. And of course, I mean, these two operations are, if you think of it as group elements, they have order too. So when you take their squares, you get identity. You can multiply both of these, so that's AB. So I'm just going to call this as C. C is equal to AB. So it appears that this is basically a reflection across XY plane. So this essentially changes Z with minus C, right? So there are two reflections and one rotation. Okay, so I'm just going to write down the group like that. So this group is called C2B, right? So that's basically contains the identity A, B, and all C. This is the same thing as what we have actually called as the Klein-4 group. It's the dihedral group D2. It's isomorphic to the dihedral group D2. If you remember, this has the multiplication table like that. This is abelian. So basically the product of any two elements is equal to the third element. Product of any two non-identity elements gives us the third, right? And if you remember, this was also the symmetry group of the rectangle. So BC is CB is equal to A, right? So, I mean, the groups are different. The symmetry group of the, let's see, so that's the symmetry group of a rectangle, if you remember. But in the case of symmetry group of the rectangle, I think we have considered this as a subgroup of SO2. So as a result, it contained two reflections and one rotation. But we also have a similar situation in here. Right? But in that case, we just consider these as elements of the three-dimensional rotations. In any case, so the groups are identical. The groups are isomorphic. Not identical, but isomorphic. So you actually meet this kind of notation a lot in applications. So there are many groups that have the same structure, but they have different names because of this, like C2Vs, for example. I think there are like other examples like C2H or things like that. They have the same structure, but somehow they are different groups. Okay. So in any case, it appears that this has I mean, this is abelian group. So therefore, this has the character. So let me call this as the character table. Okay. So E, A, B, C. Yeah, here people are using some specific notation. So they just call the representations as A1, A2, B1, B2. There's some historical reason for why these letters are chosen. I think there are like some kind of a paper in 1930s that somehow listed all of the physically interesting groups and their character tables. And people are using the notation in that paper. So as a result, a lot of people are actually using the same notation. Okay. So as a result, this is some kind of a convention, and so we would like to follow the convention. So it appears that A1 is the trivial representation. All of them are one-dimensional because this is an abelian group, so we don't have any other option. And so it appears that the representations are like this, right? Okay. Yeah, it's whatever it is. So there's some kind of a representation in there. In any case, so let's just go back to the molecule. For the case of vibrations, this is what we do. I think I'm going to do it like this. So that's color gray. So that's the oxygen. These are the hydrogen atoms. Okay. So there are 3 atoms in here. And each atom has 3 possible displacements because they are, I don't know, I mean, they are just going to displace in any direction. So this might be displaced like that. So as a result, it has a displacement of x1, y1, and z1. This might displace like that, and this might displace like this, right? So, so let's call this like x2, y2, z2. And this is x3, y3, z3, okay? If you then think about it, the x, I don't know, I think I'm going to call this as u. This is basically the displacement of the system from its equilibrium position. X2, Y2, Z2, X3, Y3 is Z3, okay? So that's the displacement of, let's say, molecule of system from equilibrium position. So the equilibrium positions are basically symmetric, but if this is displaced from the equilibrium positions, of course, the molecule will not be symmetric anymore. In any case, the restoring forces and things like that, in that case, is going to depend on that displacement. But because since the equilibrium position has this symmetry, the laws that govern how that displacement return to the equilibrium is somehow symmetric with the same symmetric group, right? I express it in a complicated way. In any case, so as a result, we have a displacement which is an element of a 9-dimensional vector space, okay? And the symmetry operations basically induce some kind of a representation in here. So symmetry operations basically transform this displacement to some other displacement, which is given by, let's say this is the group element G, by some kind of a linear mapping here. So A is basically, right, it's a 9-dimensional representation of group C2V, okay? Okay, so in any case, so therefore the job in here is to decompose A in terms of, why did I call this as A? So let me just change, yeah, it doesn't matter what the notation is. I think in the videos I'm using some other notation. Jones used the D notation for that representation, but in any case, it doesn't matter because I'm not going to solve it in here. So we need to decompose in A in terms of the irreducible representations by using the character table. This can be done. So I'm doing this, but I suggest that you also do that as well. Okay. So it appears that, should I write this thing down? I'm not sure about this. In any case, it appears that this decomposition is this. Basically, we have three trivial representations, 1A2, 2B1, and 3B2. Okay. In any case, so there are actually 9 modes, and these 9 modes decompose into these irreducible representations in that form. So in a way, these are, I mean, each letter represents a particular subspace of this huge 9-dimensional vector space. So in each of these subspaces, somehow in each of these subspaces, somehow this oscillation pattern has some kind of simpler properties, right? So as a result, if I want to choose some kind of normal mode coordinates, then I have to use these subspaces. That's what we need to do, okay? But there's a subtle issue in here. Just as in the previous problem, we had a mode with 0 frequency. In here too, there are modes with 0 frequency. Let's say it like this. There are 3 modes, 3 translation modes. And 3 rotational modes. Let's see, with 0 frequency. What are these modes? So these modes are like these, for example. So I think I'm going to show it like that, okay? Yeah, let me show it like this. So this is the molecule. This is the displacement pattern, for example. I think this is one of the representations where all of the atoms displace in the rightward direction by the same distance. This is not A1. I don't know if it is B1 or B2. In any case, this basically transforms according to one of these irreducible representations. But this is a displacement where, well, it's basically a simple translation. In that case, the potential energy of the molecule doesn't change, no compression of springs and or extension. So therefore, the springs are not involved in here. So the, I don't know, the molecular vibrations are not involved in here. It's just a displacement mode. If the molecules have this velocity, let's say, in this mode, in that case, it's going to keep moving with the same velocity. So this is the translation, one of the translational modes, for example. And as a result, this has to be associated with 0 frequency. And then there are these rotational modes. I don't know, for example, the rotational mode where this is rotating like that, or rotating like this, for example. There are these modes in here. Let me kind of draw it like that in here. This is also a mode with zero frequency, okay? So somehow we can identify all of these modes and the corresponding irreducible representation. So it turns out that some of these irreducible representations, I mean, you can identify which one of these correspond to these translational rotational modes. And so as a result, you are left with only 3 modes with non-zero frequency, okay? So there are only 3 modes with non-zero frequency. Okay. Yeah, it appears that these are like 2 of them are trivial representations, and one of them is a B2 mode. Whatever it is, so if you just look at these videos, I also identify what these modes are, because once you eliminate all the unnecessary modes, then you actually find these, the modes of interest. So there are these banding modes where the, yeah, whatever. I mean, just watch the videos. So I'm not going to talk about these anymore. But if you look at them on the web pages like the vibrational modes of water molecule, you can see nice pictures about what these modes are and how the atoms are oscillating in which mode pattern. You can easily find these. So there are these stretching modes, and asymmetric stretching mode, and symmetric stretching mode, and the bond bending modes. And it appears that, well, this is actually quite well known. So there are actually 3 frequencies corresponding to these modes. And they are in the infrared region, of course. We don't have any absorption line in the visible part. We know that water is transparent, right? No absorption in the visible part, but there's some kind of 3 frequencies in the infrared region where the water molecules actually absorb and emit light at these frequencies. So the water is not transparent in the infrared. Whatever. I mean, this is one of the things which is quite well known, because water is a molecule that that's everywhere. So as a result, this is one of the things that are well studied. Okay. So this is just a summary of what is there in the videos. But I'm not going to go in here because I know that this is going to take a lot of time. Why a lot of time? Because we are working with these kind of vectors in here, 9x1 vectors. I mean, writing them down takes a lot of time, right? But what I suggest is that you actually do it by yourself. Try to do it by yourself. So if you are stuck, then just look at the videos. Right? In any case, so you can get perhaps the ideas from the videos, and then stop the video and then try to do it yourself. So only in that way you can learn about it. Okay. So having said that, I'm going to stop here and say that I'm finished with the vibrations. So I'm not going to talk about the vibrational problems anymore. But let me talk about this. I'm going to be back with the theory. Theory of representations. This is the abstract case again, representations. I'm just going to consider some kind of a representation. So let A be a representation of group G. So the question is, how can we let's say, yeah, I'm just going to say find the invariant subspaces. Okay, I mean, if you remember, the question was like, we can find the decomposition of the representation, because once I know the characters, I can, by using the orthogonality of the characters, I can find out how many times a given irreducible representation appears in A, right? I can find that. So I can find the numbers of each irreducible representation. But actually finding the invariant subspace corresponding to a given irreducible representation, this is difficult. And so therefore, the question is, how can we find the invariant subspaces? Let me say corresponding to the irreducible representations in here. How can I undo? Yeah, all right. All right. How can we find invariant subspaces corresponding to irreducible representations of A? Okay, so that's the question. I mean, it's not just any invariant subspaces. Any invariant subspace is the minimal ones, right? So as an example, for example, right? It is this one, for example. I can easily find the decomposition of a given representation in terms of irreducible representations, but this is a decomposition in a 9-dimensional vector space. So the question is like, what is the vector that transforms like A2? What are these two vectors that transform like B1, for example? Okay. How can we really identify these subspaces? So if the original vector space is huge, very large, like this one in here, in that case, I mean, there has to be some kind of a systematic way of identifying what these subspaces are, because this is actually quite a difficult problem, right? I mean, for these two double oscillator problem, we could easily identify what the invariant subspaces are by just inspection, right? It was not a big problem. It was not difficult. But in a 9-dimensional vector space, that would be difficult, right? So as a result, there has to be a systematic way, and that's the one that I'm going to talk about this in here. Okay. So the answer is, right? Let's say it like this. We can define some projection operators I'm just going to use this letter P, right? Let's say from the representation matrices. Let's say A of G. Okay, let me write it down like that. Why do I use this funny symbol? Because there are too many things that I'm writing down. So I would like to be able to distinguish the vectors from numbers and from matrices and things like that. So as a result, I'm going to use a different representation for each kind of an object, okay? And otherwise, there's nothing special about this. So there's something called a projection operator. I'm going to describe what these things are, right? But before that, I'm just going to do some kind of a thing. So as a result, I'm just going to assume this, right? First of all, let G be a finite group. Okay, U mu of whatever. These are muth irreducible representation. And I'm just going to assume that U mu is unitary. These are unitary representations Okay, I just assume that this is the case at the beginning, so I always use this. Okay, I think so. I'm also going to use this uh, representation like this is the dimension. Okay, so I'm going to then talk about this A in here. Let A be a unitary representation. Why unitary? Because I don't want to deal with the other cases, right? So unitarity has some nice properties. So let A be a unitary representation of G. Okay. So I know that this A is decomposable in terms of the irreducible representation. So therefore, this is like M1 times U1 plus whatever, M2 times U2 and so on. And the question is like, how can I find subspaces which transform like U2, for example? Okay, that's the question that we would like to uh, answer. So there's this definition in here. Sorry about this. I'm just going to do this notation, right? So that's the notation. Operators, matrices, and whatever. These are basically, I'm going to use this notation, A, B, whatever, this notation. Vectors, I'm going to use the cat notation, okay? So as a result, I'm doing this just to distinguish the different kinds of objects that we are going to have. And the numbers are like basically, I mean, these are operators or matrices on this vector space where A is defined, right? Just think of it like this. And the vectors on that vector space is E. So, okay. But there are also these small representation matrices in a different dimension. I'm just going to use the regular notation for these. Okay. So definition. Yeah, let me say it like this, representation of G. In vector space V, for example. So these are operators and matrices on the vector space. I'm just going to use this notation. Vectors in V, I'm going to use this notation, okay? And probably that's a little bit clear now. Okay, so the definition is like for vectors in that vector space, I'm just going to define this. So a set of, this is an ordered set of an ordered list of vectors, let's say E1, E2, dot, 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 ED mu is said to be an irreducible set transforming like the mu era. So the number of vectors should always be equal to d mu. Let me underline this. It's an irreducible set. I'm going to call this as an irreducible set. And if I, but the set is defined with respect to this corresponding irreducible representation. So as a result, sometimes I'm going to say that, well, this set is transforming like the meter is irreducible representation. If the following property is satisfied, so that the property is this. So if I apply the representation operator on any of these vectors, I get this. It's just a linear combination of all the other vectors, but the coefficients that appear is basically the mute representation. Sorry about this. No, complex conjugate. EJ. Okay. So let me box this because I'm going to construct this other things on top of that. So there's some kind of an unusual order in here. So there's like the, the, the symbols are like JI in here and EJ in here, where the symbol which is summed, this J index, appears first in here, right? A lot of people actually write this in the opposite order. Well, this is incorrect, right? So the correct one is this. Okay. So in any case, so I mean, we just give a name to an idea. So let me say that if that's the case, in that case, the subspace spanned by all of these vectors, E1 dot 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 ED mu, is an invariant subspace. Okay. It's an invariant subspace, right? Because if you apply this representation matrix to any linear combination of these vectors, you again get another vector in the same subspace. So therefore, this subspace is invariant, right? And so therefore, finding invariant subspaces can be reduced to that problem of identifying such irreducible sets of vectors. Okay, we can think of the problem like that. All right, there is this nice thing in here. I think I'm going to call it like that, right? Let's do it like this. So this is the next property. So let's say it like this. Let E1 dot 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 ED mu is an irreducible set transforming like the muth irreducible representation, right? I don't have much space. And let's say that F1 to dot 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 F D nu is another irreducible set transforming like some other irreducible representation. They might be the same or they might be different from each other. So the theorem is this, basically. If mu is different than mu, I mean, if these irreducible sets correspond to different irreducible representations, then they are orthogonal to each other. So that's the first thing. Second, if they are transforming like the same representation, I mean, I have two irreducible sets and both of them are transforming like the same representation, okay? Then it appears that this Fij dot product is equal to basically C times delta Ij for some C. Basically, it means that for example, the first vector is always orthogonal to the second vector. and so on. Even if these two irreducible sets are different irreducible sets, but they are still transforming like the same representation. Okay, and the proof is basically goes like this. I'm not going to show this. Let me spend some time on this in describing this. So I'm just going to define some kind of matrix. So define the matrix Xij by the inner product of these two expressions. Okay, and then look at this Fi A of G Ej. Just look at this expression. I can expand this in two different ways, right? First of all, I can think of it like A applied on Ej, so therefore this is going to be like Fi-Ej. I'm just going to quickly write this thing down, so therefore this is Ul, sorry, F-I-E-E-L U-L-J mu G. And I'm going to, and then you can look at it like this. A of G is applied on this Fi in here, but in the opposite way. So to be able to do this calculation, you have to take the Hermitian conjugate of that part and do the analysis correctly and then revert back. But you can show that this is equal to basically U nu of I m G Fm Ej dot product. So you can basically show that by using this. I'm not going to show this, but I'm going to ask you to show that. Right? Just show that this matrix satisfies that property, and then we use Schur's lemmas. Sorry, Schur's lemmas to deduce basically this property in here. But I'm not going to do this step, so I'm just going to ask you to do it yourself. But once you get this, you basically reach to that result easily, right? If the representations are different, then this matrix X has to be a zero matrix. Definitely the case. If mu and nu are equal, then this X matrix is just a multiple of identity. So this result basically expresses this fact. Okay. So let me kind of show it like this so that we include everything in here, right? So let me stop here. Let's take a break. After the break, we are going to see how we can use these. I'm just going to define this projection operators that basically gives us the vectors in these irreducible sets. Okay. Let me stop this video in here.